technology where we can program it even after the manufacturing. So today we are going to discuss on how this FPGA technology can be implemented into autopilot system of unmanned aerial vehicle UAV.
In order to build the autopilot system in the UAV, there are several challenges that we need to face, and in order to get a better result, we have to overcome these problems. The challenges that have been mentioned earlier are high-level planning, D capabilities, sensor fusion, sensor integration and diagnostic, conventional servo and actuator motor. As you can see on the screen, these are some of the suggestions to overcome the problems. The first one, we need a separate computer microprocessing. The second one, by using FPGAs in order to maximize the parallel processing capabilities and analog signal conditioning. The third one, we also need a computationally intensive calculations and massive sensor data and signal processing. And the fourth one is a flexible autopilot should be a stand-alone system that does not require in-depth knowledge of analog or digital design and low-level programming languages.
Now, let's move on to the type of processing system that have been used in UAV. For your information, actually there are so many types of processing system that already been adapted into autopilot system. But here, I just only want to stress out on 3 types of processing system that are widely used in the aviation world nowadays. For the first one, there are DSP low microprocessor, full computer implementation, and also the implementation by using FPGAs.
As we can see on the screen, these are the comparison of the advantages and disadvantages of the 3 types of processing system that have been mentioned earlier. For the first one, let's take a look at the full computing system. Basically, full computing system has such an excellent processing power. It is also proved to work successfully, but remember, a great care must be taken in programming the control system, or the real-time requirement will never be met. This requires not only a great deal of knowledge of control systems, but also knowledge of the real-time programming language. The second type of processing system is microprocessor DSP low power autopilot. This type of processing system has only one single processor, and sadly, this system cannot be operated with parallel processing. And such a great care must be taken to be sure that each of the asynchronous sensor inputs are sampled at the correct time, while also updating the servo outputs. The majority of the implementations did not allow for Simulink integration or hardware in the loop. And for the last one is the comparison of the FPGA implementation. FPGA implementations have benefited from the flexibility and parallel processing capabilities of the FPGA in regards to manage input-output function. How this implementation of FPGAs in the autopilot system going to be works? First, we have to think about the design of the FPGA itself, and here is the proposed design. A Z-Link Vertex 2 Pro FPGA is being selected as the autopilot primary processing platform, and these processors deliver DSP capability and can operate with clock frequencies that can exceed over 300 MHz while operating in parallel with the FPGA logic slices. The autopilot is fully interfaced or integrated with Simulink, capable of handling several types of communication protocol, accepting various ranges of analog sensor input, data acquisition by including additional memory, measuring altitude, and also forward speed through onboard pressure sensors, allowing for releasing control of the physical system to either a master computer or a human pilot. And now, we will discuss on how this FPGA works in the autopilot system. As you can see on the screen, This is the simple schematic diagram to describe the working principles of the FPGA. Basically, this system will start with the programming languages, and then they will go to VHDL compiler before going to the gate level simulations of C to VHDL translations. And right after the process, they will go for the validation hardware operations. From what we can see on this picture, the system is started to work by designing the desired circuit in the Simulink and done the simulation. After that, the data from the Simulink will fully integrated and interfaced by the FPGA through the serial ports, and data will automatically saved by the memory in the FPGA. The separate microprocessor will work in order to make the system run smoothly. By that, it will process and convert the data into hardware to run all the components parallel, including in the control of servo to all part of the control surface system. The board designed for this FPGA are separated into two multifunctional boards, that is main board and also the secondary board for backup in any emergency case. For your information, the size of the board based on the selected circuitry is approximately the size of a credit card.